Okay, so let's talk about the left regular representation. Sorry, the left regular action. Okay. So groups acting on themselves by left multiplication. Okay, so so we have a group G which acts on itself such that an element G is acting on an element A by G multiplied with A. So basically speaking, so this GA is basically the multiplicative operation the multiplicative operation on groups. Nothing else, sir. This is the simple multiplicative operation on groups. So if the group is an additive group, that is if G is additive, then this action is basically G acting on A is nothing but G plus A. Clear? Okay. Okay. So so in the first lecture regarding the permutation representation associated with a certain group action, let's see some consequences. Okay. Notice that so suppose G is a group and G acts on itself. Then how does this action typically work? That is what I mean to say. So if G is a finite group, let's say, so if G is a finite group, say, then we can index each element of G with some natural number, right? So let us do it in the standard way. So suppose G is G1, G2, G3, let's say till Gn. So it is quite obvious that if you choose an element G from capital G and you consider this action, then for all A in G, this G acting on A, which is the multiplication GA, so this GA element is again in G, right? Again in G. So we can think about this like G acts on some GI and it is some element GJ, right? Where I is obviously greater than equal to 1, less than equal to n, and J is also greater than equal to 1, sorry, less than equal to n and greater than equal to 1. Yeah, correct. Right. So basically, if I consider the associated permutation representation afforded by this action, so let sigma G be the associated permutation representation afforded by the action, then sigma G can be thought of as simply mapping the index I to the index J, right? This is very trivial to notice, because if you remember what the associated permutation representation was actually doing, so basically if G acts on a set A, then we know that this action is basically a mapping from G cross A to A, right? So we are defining a mapping sigma G where G is a fixed element from capital G. So we consider this to be a mapping from A to A such that sigma G maps an element small a to the element G on A, right? And by the way this sigma G is represented, then sigma G has an inverse mapping also. Okay, and since the domain and codomain are same, sigma G has an inverse mapping. So sigma G is basically a bijection. So if it's a bijection, then this can be viewed as a permutation of the elements in A. Okay. So sigma G is basically can be also thought of the image of the element small g in Sn or in any symmetric group. So we can think of this sigma G as a mapping from, rather I should say the image. So if I consider a map from G to SA, where SA is the set of all permutations of the elements in A, then we can map G to sigma G. Yeah. So these things were covered in the previous lecture as far as I remember, in the first lecture on group actions, right? Yeah. So sigma G is basically, so if I map sigma G as this associated permutation representation, then sigma G of Gi by this statement is nothing but Gj, but that is equivalent to just getting mapped I to J, right? So that is what we did here. Yeah. Thus, we can say that sigma Gi is equals to J if and only if G acting on Gi is equal to Gj, but that is by definition G multiplied with Gi is Gj. Yeah. Okay. Well, let's consider a few examples straight away. Okay. So example 1. So we will consider the Klein 4 group. Okay. So it consists of 1, A, B, and C, where obviously C is nothing but the element AB. Okay. So the properties are that every element has order 2. Every non-identity element has order 2. So you have A squared equals to B squared equals to C squared equal to 1. And 1 is obviously the identity element of this Klein 4 group. Clear? So let G be equal to K4 and G acts on itself. So as I said that this very action is also called the left regular action of G on itself. Okay? So G equal to K4 and G acts on itself. Then let A in G be fixed. Okay, this A is this element A. Okay, then first notice what is A acting on 1. So A acting on 1 is A. Now A acting on A itself, so it is A squared and it is 1. Then A acting on B, so it is AB, but we have considered AB to be C. And A acting on C, so this is basically AB, but this is A squared B and this is B, right? Now suppose we index this set K4 as G1, G2, G3 and G4 such that G1 is 1, G2 is A, G3 is B and G4 is C. Thus if I consider the associated permutation representation afforded by this action with respect to this element A in G, this A, then what is sigma A of 1? Then sigma A of 1 is basically the index which we will be eventually getting on mapping sigma A of G1, right? So what is sigma A of G1? So sigma A of G1, or rather let me write it like this, it will be better to understand. So what is sigma A of G1? So sigma A of G1 is nothing but A acting on G1. But G1 is being considered as 1. So this is A acting on 1, which is A. And A has been considered as G2. So this is equals to G2. Thus sigma A of G1 is equals to G2. Therefore, the sigma A mapping sends 1 to 2. So 1 is getting mapped to 2. Clear? Similarly, what is sigma A of 2? So sigma A of 2 is basically sigma A of G2, and that is equal to A acting on G2. But G2 is A itself, so it is A acting on A, which is A squared by left multiplication, and A squared is 1, but 1 is G1, right? So if I consider the index, then that is being considered as 1. So 2 is being sent to 1, right? So 1 is being sent to 2 and 2 is being sent to 1. And similarly, what is sigma A of 3? So sigma A of 3 is basically sigma A of G3, but that is A acting on G3, but G3 is B, so this is A acting on B, which is AB, but AB is considered as C, and C is considered as G4, I guess, right? G4. So the index is 4. Therefore 3 is getting mapped to 4, and similarly you will notice that sigma A of 4, which is sigma A of G4, which is A acting on G4, which is A acting on C, and A acting on C is B, so it is equal to B, and B is G3. So the index is 3. Obviously, there is some abuse of notation being going on here because we cannot write G3 is equals to 3, right? But we are just writing that to show the correlation. So that means 4 is getting mapped to 3, right? Therefore, this sigma A, so we know that sigma is a permutation, right? So sigma A has this permutation representation as, so 1 goes to 2 and 3 goes to 4 and comes back. So this is a cycle representation of sigma A, right? So this is the cycle representation of sigma A. Cycle representation of sigma A. Clear? Okay. So sigma, so what is the cycle representation? If I be very short, so if you write, a structure of this form, let's say I1, I2, I3, so on till Ik, where each I1, I2, I3 are some natural numbers from within certain range, starting from 1 to some range, let's say n. So this typically represents the mapping which sends I1 to I2, I2 to I3, I3 to I4, and so on till you have Ik minus 1 to Ik, and Ik is mapped back to I1. Okay, so that is what is happening here. Okay, so one is sent giving, one is mapped to 2, 2 is coming back to 1, 3 is getting mapped to 4, 4 is coming back to 3, and we know that the mapping which sends 1 to 2 and 2 back to 1 has nothing to do with the mapping which sends 3 to 4 and 4 back to 3. That is the reason why we can write both these cycles. So this forms an individual cycle, this forms an individual cycle. We can write them as products. So product in the sense, if you consider this to be a mapping, let's say F, this to be a mapping, let's say G, then these two mappings are composed. We write that as a multiplication of the cycles. These are the topics which we will surely cover if I come, bring out a lecture on symmetric groups. Clear? Okay. Now, now let A be the set of all left cosets of some subgroup H of G. Clear? Consider G acting on A. So how are we having this action? So G acts on the element, let's say small a H, by the coset GAH. Clear? For all G in G and A in H. Clear? Now obviously, if H is the identity element E, identity trivial subgroup E, then AH is nothing but the singleton set A. So you have the set A, capital A, to be the singleton set A, right? So if we represent this singleton set as A simply, then G acting on A is nothing but the action of G, but the action of G on itself, action of G on itself by left multiplication, right? By left multiplication. Sorry, I have written this wrong. A cannot, so A is not the idea, is not only containing the sorry, the singleton set A. So it is the collection of all singleton sets A such that A is in G. Yeah. Right? Okay. Now this is very trivial to notice. Okay. So now suppose H is a subgroup of G and the index of H in G is n. Okay, n is a finite number. Then obviously the elements of A can be listed as say A1H, A2H, and so on till ANH. Then again, if we consider the action of G on A by left multiplication, then the associated permutation, say sigma small g of some index I is equals to some index j if and only if G acting on AIH is equals to AJH. Clear? But this AJH nothing but GAIH. Right? And I should mention here that in this case G in capital G is fixed. Clear? So obviously whatever we had done in the case of G acting on itself by left multiplication, we can do analogous things if we consider the action of G on the collection of all left cosets of a subgroup H in itself. Clear? Okay. So let us straight away consider an example. So we consider this at D8. Let G be D8. So D8 is basically the collection of the elements 1, R, R squared, R3, S, SR, SR squared, SR cubed, where R represents reflections and R represents rotations and S represents reflections. Okay. So if I again use an example of this, so this is the set of all symmetries of a regular foregone, right? So consider a square. Okay. So consider a square. So suppose I index this 1, 2, 3, and 4. So R is a mapping. To be very specific, this R represents a mapping which sends the index 1 to 2, 2 to 3, 3 to 4, and 4 to 1. The other way of saying this is that we are rotating the square by 90 degrees to the right. I mean 90 degrees clockwise. Okay. So if you reflect it twice, that is you send 1 to 3, 3 to 1, then 2 to 4 and 4 to 2, 2 to 4 and then 4 to 2. Then that's basically your R square. So you are reflecting once and then again. Similarly, R cubed, right? So in R cube, you are sending 1 to 4, and 4 to 1, 2 to 3, and 3 to 1, 3 to 2, right? So if you similarly, if you consider the reflections, let me put up the slides. So what are the possible reflections of a square? So visually, it is very clear that along this diagonal you have a reflection, along this diagonal you have a reflection, along this line passing through this center have a reflection, and this gives you a reflection. So there are 4 reflections. So SR square, SR cubed are the 4 possible reflections, and 1 R squared, and R cubed are the 4 possible rotations of a square. Clear? Okay. So we have considered this group. Let H be the subgroup generated by S. So it's simply 1 and S. And why is it so? Because the properties of the rotations and reflections in the dihedral group are that R has order 4 in this case. So you have R to the power 4 is equals to 1. And S in any dihedral group has order 2. Clear? So if I speak on a general sense, the D2n is the set which is generated by R and S such that R to the power n is 1, S squared is 1, and SR is equals to R inverse S. So these are the properties. Clear? Okay. So since the order of S is 1, so the group generated by S is only 1 and the element S itself. Okay. So what is the index of H in G? So we know the index of H in G is nothing but the order of G divided by the order of H. So that is equal to 4 because the order of G is 8 and the order of H is 2. So if you consider A to be the set of all left cosets of H, then they are basically, so you have 1H, right? Then you will have RH, then you have R squared H, and you will have R cube H. Clear? These are the possible left cosets. Now we want to see what the action of G on A does. So let G act on A, and let A be having the elements indexed as A1, A2, A3, A4, where so A1 is 1H, A2 is RH, A3 is R squared H, and A4 is R cube H. Clear? Then let S in G be fixed. Okay. Let S in G be fixed. Consider the associated permutation representation afforded by this action. So let that be sigma S. So what does sigma S does to A1? So that is basically the action of S on 1H, and that is equal to SH, right? That is equal to SH. But SH is nothing but H, right? Because S is contained in H. H is the set 1S. So S is contained in H. Therefore, SH is nothing but H, right? And H is represented by the element A1 itself. So it's A1. Therefore, sigma S sends the index 1 to 1. Clear? Similarly, with what is sigma S of A2? So A2 is the set RH, sorry, the left coset RH. So this is SRH, right? So this is SRH. Clear? But if you use the property, then SRH is nothing but R cube H. So it is R cube H. Okay. So R cube H is A4. Right. Therefore, sigma S of the index 2 is nothing but 4. So let this be 1. Let this be 2. Now note, for this moment, just consider these things as facts. Okay. I'll try to bring out a detailed lecture on the groups D2n and the groups Sn, and there every such thing will be clear. Similarly, if you have sigma S A cube, then this is S acting on R squared H. So this is SR squared H. but SR square H is basically, so it will become SR square H only. So it's R square H. SR square is R square H. So R square H is A3, right? Therefore, sigma S sends 3 to 3. And similarly, you will notice that sigma S sends the index 4 to 2. Therefore, how can sigma S be represented? So let us just notice. So sigma S sends 1 to 1, 2 to 4, 3 to 3, and 4 to 2. So this is the simple cycle 2, 4. Right? Clear? Okay. Okay, so we have discussed enough examples. Let us come to a theorem related to this action. Okay. Theorem. Let G be a group. Let H be a subgroup of G, and let G act on A, where A is the set of all left cosets of H in G. Clear? Let pi H be the associated permutation representation afforded by the action of G on A. Then the first point is that G acts on A transitively. So if you know, if you remember what a transitive action is, so transitive action is basically that action which consists of only one orbit. Okay. Number 2, G1H, that is the stabilizer of the element 1H, is a subgroup of H. And number 3, that the kernel of the permutation representation pi H is the intersection of the elements in X, H, X inverse, where X belongs to G. And this is the largest normal subgroup of G contained in H. Okay, so let's prove this statement. Wait a second. Yeah. Okay. So G acts on A transitively is the first thing which we require to prove. Okay, so what we can actually prove is that if you consider any two elements from the set A, then they lie in the same orbit. Okay, so let's start with the proof. So proof of 1. Okay. Yeah. So let AH and BH be from A. We consider G to be the element BA inverse. Then what is G acting on AH? Then that is GAH, but that is exactly BA inverse AH, and that is equal to BH. Therefore, so if this happens, that means, so if you go by the definition of an orbit, which I hope you know, because I have discussed enough about orbits as equivalence classes and orbits independently in the last 2 lectures. Therefore, there exists an element G in capital G such that B can be represented as G on A. And so typically that means B and A, or rather I should say, so I should use the term BH here and AH here. So that implies BH and AH are in the same orbits, are in the same orbits. Since they are arbitrarily chosen, right? Since BH and AH are arbitrarily chosen, the action has only one orbit. The action has only one orbit, because if you choose any arbitrary two elements from the set A, they all fall under the same orbit. So there is only one orbit which contains every element in it, right? So the action has only one orbit. Therefore, G acts on A transitively. Clear? Let us move on to the next proof. So what is the next statement? So the next statement says that the stabilizer of the element 1H is contained in H. So let's go direct by the definition. What is the stabilizer of 1H? So it's the collection of the elements small g such that G fixes the element 1H, right? Right. So it is equal to 1H. But that is exactly the set of elements G such that GH is equal to H. But that is the set of elements such that G is in H. So that means this is the set H, right? Or I should say it is contained in H, right? So if you choose any element from G1H, that is in H. That is what I wanted to speak about. So therefore, G1H is a subgroup of H. I can obviously use the term subgroup because G1H is a subgroup of G, H is a subgroup of G. G1H is contained in capital H, therefore it's a subgroup of capital H. Okay. Now let us move on to the next proof. So what is the kernel of pi H? So kernel of pi H is basically set of the elements G in capital G such that pi H of G is equal to the identity element, right? Right. So kernel of pi H is the identity element. So basically, so it is the identity element of the permutation group, right? But that is basically the set of elements which map XH to XH, right? Right. So that means, so it is the set of elements G such that X inverse G X of H is equal to H, right? Therefore, this is the collection of elements G such that G is contained in XH X inverse, and this happens for all X in H. Sorry, for all X in G. So obviously, this is the set of all intersections of the set XH X inverse such that X is iterated through the sets. Clear? Right? Okay. Now, why is it a normal subgroup? Because we know that the kernel of any permutation is the normal subgroup of its domain. So it's normal in G, and H is a subgroup of G. So kernel of pi H is contained in H, obviously, right? And kernel of pi H is contained in H. It is very trivial to notice from this exact thing, right? So that implies kernel of pi H is normal in H. Clear? Let me complete the proof here itself. Now suppose you consider another normal subgroup in H, okay? So let N be normal in G such that N is in H, okay? Okay. Then N can be written as XH X inverse for all X in G by the normal property. But that implies N is contained in the intersection of all these elements XHS inverse, right? Such that X is contained in G. And this is exactly the kernel of YH. Is it clear? Is it clear? So the next one, next theorem we are talking about is of high importance. I had also discussed about this in the previous lecture where I discussed uh, on the action of a group on itself by conjugation. Yeah, by conjugation. There also I had a brief discussion regarding this. Okay, so it's called the Cayley's theorem. It's called the Cayley's theorem. Okay, so it's very easy to observe what happens. Okay. The theorem is very simple. Every group is isomorphic to a subgroup of some symmetric group. To a subgroup of some symmetric group. If the order of G is n, then G is isomorphic to a subgroup of Sn. Subgroup of Sa. Clear? Okay. So let's come up with a proof of this. So proof. Now, what did we have in the previous theorem? Okay. So what we do is in the previous theorem, we just consider H to be the identity subgroup in the previous theorem. That will do. Because if you consider this mapping from G to SG as a homomorphism, then we know that every such mapping induces an action, right? Then the kernel of this mapping, it will be contained in H, and H is nothing but the identity subgroup. That means the kernel of phi should be the identity subgroup, but that implies phi is 1 1. So if phi is 1 1, that typically implies that G is isomorphic to some subgroup of Sn, Sg. Typically G is isomorphic to its image. Clear? Image in Sg. Because what we had discussed in the starting of this group action series, that provided any action you have, you can associate a homomorphism from the group G to SA, right? So what I mean to say is that, let me change the color. So I'm writing it somewhere here. Okay. So if G acts on A, then you can associate a homomorphism which we had written as sigma G, which maps, so which acts as a permutation of the elements in A, right? Or rather I should say it as, so you can have a homomorphism phi from G to SA such that phi maps every element small g to sigma G. Sigma G is the associative permutation representation. And on a similar note, if you have a homomorphism given as phi from G to SA such that phi maps G to some permutation sigma G, then associated to this sigma G, you can just process an action of G on an arbitrary set A. A is the set of all elements whose permutations are inside SA. And that is pretty analogous to understand, right? So here we are considering the set A to be the set of all left cosets of G. with respect to the subgroup H, left cosets of H with inside G, and H is consisting of the singleton set, the trivial subgroup. And previously we had discussed that if H is the trivial subgroup, then what is A basically? So A is the collection of all elements G in G. A is typically G, or I can consider the each left coset of H, each left coset of H, which is the set A, as the element A itself, right? So that is what we are doing here. So we are actually inducing an action G on itself. That is what we are actually doing. Clear? So that means that every group you have, that you can associate it with any permutation group, because we know that subgroups of symmetric groups are permutation groups. So we have just proved the fact that every group is isomorphic to some subgroup of a symmetric group. That means every group is isomorphic to a permutation group. That is, every group can be viewed as a permutation group. Okay, and that is what actually the historical approach of group theory was. So every group was historically approached as a permutation group. Groups were studied as permutation groups. The modern approach is a bit different, obviously, because we have more tools in hand, and certainly if you have a large symmetric group, then studying those permutation groups are very complex. So that doesn't give you the right approach to studying group theory. Obviously we have much larger tools at this moment, therefore the modern approach is a bit different from what we used to do. Okay, so the corollary of this theorem is what more important, I would say, because it also helps in characterizing certain groups. So let's come to this. So if G is a finite group of order n, and P, so P is the smallest prime, P is the smallest prime dividing the order of G, that is, P divides the order of G, then any subgroup of index P is normal. Clear? So what are we actually saying here? So if G is a finite group of index n, that is, number of elements in G is n, and P is the smallest prime factor of n, P is the smallest prime dividing n, okay, then any subgroup of G such that the number of distinct left cosets of that subgroup in G is P, that is the other way of saying any subgroup of index P, so that subgroup will be normal. That is what we are going to speak about. Okay, so let's prove this. Proof. Okay, suppose H is a subgroup of G and the index of H in G is equal to P. Then let pi H be the permutation representation afforded by multiplication on the set of left cosets of H in G. That is the same action which we were speaking about since long. That is the action of the group on the set of all left cosets of the subgroup H in G. Okay, and pi H is the associated permutation representation. So it's the associated permutation representation. Clear? Clear? Now let K be the kernel of pi H. And we know that the kernel of pi H will be contained in H, right? That we have studied. What we do is, so kernel of pi H is a subgroup of H. So that means we can form the index of the kernel of pi H in H, right? So let index of kernel of pi H in H be K. Okay. Then we have a very important property of index of subgroups. So it's the index of H in G can be written as the index of K in G. Sorry. So the index of K in G can be written as the index of H in G times the index of K in H. Right? Clear? And this is obviously equals to Pk. Right? Now, since H has P left cosets, then G mod K, because K is a normal subgroup of G is a kernel. So G mod K is isomorphic to a subgroup of SP, right? Because the index of K in G is Pk. What is K? K is the index of K is the number of left cosets of K in G, and P is the number of left cosets of H in G, right? Therefore, if you form the quotient group G mod K, then that can be formed as isomorphic to a subgroup of SP by the CAYLEY'S theorem. By the CAYLEY'S theorem. Clear? By CAYLEY'S theorem. Clear? Now, by Lagrange's theorem, what happens? So, by Lagrange's theorem, now since G mod K is isomorphic to a subgroup of SP, therefore, the number of elements in G mod K must divide the order of SP. Therefore, so what are the number of elements in G mod K? So, it's Pk, right? Therefore, Pk must divide P factorial. But P factorial is nothing but P minus 1 factorial. So, K must divide P minus 1 factorial. But all prime divisors of P minus 1 factorial are less than P, which is pretty obvious, are less than P. And by minimality of P, because we have considered P to be the smallest prime, right? The smallest prime which divides the order of G. By minimality of P, any prime divisor of K is such that it's greater than K. It's greater than K, right? So therefore, the only possible value of K is 1, right? So if K is 1, therefore H is same as K, and K is normal in G, right? So H is normal in G. Clear? Okay, so this was all about the left regular action of G on itself. In the next lecture, I'll try to have a discussion on the conjugates in Sn. Okay, so one sec. Yeah, so I'll try out to bring a discussion on the conjugates in Sn, and then we will move on to study automorphisms. Automorphisms are basically isomorphisms from a group G to itself. Clear? Okay, so meet you guys in the next lecture.